Welcome back. In this example, we're trying to synthesize an acid chloride from an alkene. And so we have to devise a strategy which will allow us to convert our alkene to our target compound, the acid chloride. Now, as I've mentioned in previous examples, it's important to count your carbon skeleton before you begin the question. And so if we want to count the carbons in our alkene, we have 1, 2, 3, 4, 5, 6. This would be a 1-hexene or hex-1-ene. And in our target molecule, our acid chloride, we have 1, 2, 3, 4, 5, 6. So again, hexanoyl chloride, 6 carbons. Generally, this implies that we don't have to carry out any carbon-carbon bond-forming reactions because we have an equivalent number of carbons in our starting material as in our target compound. So we should be thinking about what functional group transformations we can carry out that will allow us to go from the alkene to the acid chloride. Now, we don't have any direct pathways between alkene and acid chloride. We're going to have to devise a strategy that will take us from the alkene to the acid chloride. So there's a couple ways that you can look at this. Pulling up your charts, you'll be able to see there's various pathways that we could take between the alkene to the thionyl chloride. And that you can think about reactions of the alkene to begin with, and you can also consider what reactions allow us to prepare acid chlorides. So in a sense, you're looking at what precursor, what compound under certain conditions would make an acid chloride. We call that strategy retrosynthesis, where you're starting from your target molecule and kind of thinking backwards as to what steps may lead to that particular point. So in this example, that can be quite helpful because we only know one particular way to make an acid chloride. The most common way of making an acid chloride is from its corresponding carboxylic acid. And that carboxylic acid reacting with thionyl chloride, SOCl2, will generate the acid chloride. So I say that's an important step because when you now consider that what we need to get to in order to form the acid chloride is a carboxylic acid, we know many other ways in which we can form carboxylic acids. But the other main point that we can consider before we start devising a strategy is to consider that we do have a carbonyl carbon in our final compound. And so that should get you thinking about ways in which we can take this alkene to an aldehyde or potentially a carboxylic acid, as we just mentioned. So let's start with a possible route that we could devise for this particular compound. Now, key as well, notice how the carbonyl is formed at the terminal carbon of that 6-carbon chain. So ideally, we would like to have a new carbon-oxygen bond at this location. And so from the starting alkene, we know that we can form new carbon-oxygen bonds to the formation of an alcohol. And so now the question becomes, which conditions will give us the alcohol that we would like? And so looking at this particular alkene, we have 2 possible carbons to which we could form a OH group to those carbons. If the OH group ends up at this particular carbon, we refer to this as Markovnikov addition. If the OH group in some type of hydration reaction ends up at this carbon, then we know that's an anti-Markovnikov. So given that we want the carbon-oxygen bond to be at this terminal carbon, it would make a lot of sense to undergo a hydration reaction, addition of water across this alkene that would install a OH group at this carbon and a hydrogen at this carbon. And so we know how to do that. We can use hydroboration oxidation. So as a first synthetic step, hydroboration, this is use of borane, BH3, and THF. followed by the oxidation step, which involves hydrogen peroxide and a strong base, sodium hydroxide. And so that will result in the formation of a hexanol, a 1-hexanol, or hexane 1-ol. And so you can see that this reaction is going to give us this new carbon-oxygen bond, which will be helpful for oxidizing up to a carbonyl, i.e. a carboxylic acid derivative. So we have 1, 2, 3, 4, 5, 6 carbons. We have our OH group attached to that terminal carbon. And so now we want to think about ways in which we can oxidize this particular alcohol to the corresponding carboxylic acid. Because we mentioned earlier that one way to form an acid chloride is through the use of thionyl chloride from the corresponding carboxylic acid. So now the question becomes, what conditions can we use to convert an alcohol to a carboxylic acid? And so looking into our notes, we know that the strongest oxidizer that we've encountered in this semester is chromic acid, H2CrO4. And so you can show chromic acid as shown as H2CrO4. That's understood that you're using a strong oxidizer, chromic acid, to convert the primary alcohol to a carboxylic acid. Or, if you wish, you may show the ingredients which we must combine to form our chromic acid. So sodium dichromate and sulfuric acid and water. And so this ends up being the link between our alcohol and carboxylic acid. We know that we must prepare carboxylic acid if we want to end up with our acid chloride. This is one of the easiest and really the only way we've learned how to make an acid chloride. So this is a plausible synthetic route for the transformation of this original alkene to its corresponding acid chloride. It's a 3-step synthesis. We start with the hydration of the alkene using hydroboration oxidation so that we have anti-Markovnikov placement of the OH group of the alcohol. And then using chromic acid, we can convert the primary alcohol to the corresponding carboxylic acid. And then using thionyl chloride, once again, we can convert the carboxylic acid to the acid chloride. So in the synthetic question, and like any synthetic question, you're not showing any mechanistic details. We're not showing any curved arrow formalism to indicate how these reactions occur. We're only concerned with the reagents that are required to transform one compound to the other. And so you have this starting material. We consider these intermediate products. These are products that are formed during the course of this synthesis, and this is our final target molecule that we're after. So if you have any questions about this synthesis question or any of those that you come across when doing extra practice in the textbook, by all means, please send me a note via message or email. Thank you.